Yeah, good morning, children. Yesterday, we have discussed what coordination number as well as density of the unit cell we have discussed. And related to that problems also we have seen yesterday in the IIT class. And today we are going to discuss about what the remaining topic, what we have packing fraction. In the IIT class, that packing fraction also packing efficiency already we have discussed that. But however, the complete explanation with a good efficiency, it was might be not completed in IIT class. So the remaining topics, whatever we have, that we will discuss in this class. Okay, fine then. So packing fraction, what is meant by packing fraction in a unit cell? So packing in the sense that you know very well what is packing, how much we are going to fill in any box it if it will be there, any container it will be there, how much we can able to pack into that. That is what packing. Fraction in the sense what? So how many number of atoms or how many number of molecules or how many number of ions we may get filled into the given container. The container can be, here we are considering what a unit cell. Okay. So the matter, if you're observing here, what is the packing efficiency of a body centered cubic unit cell? So clearly we know that we have what three types of bodies, three types of centered unit cells. Yesterday we have discussed that. What are they? Simple cubic, body centered, and as well as what that is face centered cubic. Okay, so and in those three, he is asking what is the packing efficiency of a body centered cubic cell. Clearly, he has given us what the packing efficiency of body centered cubic unit cell is 68%. How we got this 68%, and what basis we are getting this 60%? That we will discuss that one. So we'll go with the definition of a packing efficiency. If you'll see the definition of the packing efficiency, what he has given, the packing efficiency is the fraction of the crystal actually occupied by the atoms, and it is usually represented by a percentage or a value fraction. So I told now the number of atoms or number of molecules or number of ions which are occupied in the given unit cell, in the given crystal, those that is called as what a packing efficiency of that particular unit cell will be. So it is usually represented by a percentage manner. How we are representing this in a percentage manner or fraction, volume fraction manner. Mathematically, how we are by using this formula. What are number of atoms? The mathematically the packing efficiency is equals to. So if in this lesson he is asking to calculate the packing efficiency of any BCC or FCC or any HCP, like that, anything he is asking, how can we calculate that? Means what? Number of atoms into volume occupied by one share into 100 by total volume of the unit cell into 100 will be. So this is the formula in order to calculate the packing efficiency will be. So what are the factors influence the packing efficiency? What are the factors are going to influence the packing efficiency? Volume of the unit cell. Let we will take a big container and a small container. Obviously, we know that as what? In a big container, we can keep more number of objects, what we are keeping. In a small container, less number of objects we can keep. So similarly, the volume of the unit cell is larger, we can fill more number of atoms. Similarly, volume of the unit cell will be less. At that time, we can keep less number of atoms will be. So that is influencing or not? Definitely. So the volume, it is going to be influence the packing efficiency. Similarly, number of atom in a structure. So whatever the container it will be, it is a large container, it is a small container. If we are taking like we are considering it as a unit cell. If the atom structure will be larger in size, we can keep less number of atoms. If the structure of atom and the size of the atom will be less, at that time in a same container we can keep more number of atoms or not. So this is also going to influence. If you have take a cricket ball and small glass balls, let take a cube like structure. One cricket ball, only one cricket ball you can keep into that, a small box we have taken. Yes or no? But small glass balls you can keep more and more. So that is the difference. These are that means what? The size of the ball, the size of the atom or ion or molecule are going to be affects this packing efficiency, and volume of the atoms also are going to be affected. So these are the factors are influencing the packing efficiency will be. So this is about what the definition of the packing efficiency and the factors influencing the packing efficiency will be. Okay, now packing phenomenon, I'll tell you what how the 68 percentage will came, and for the remaining centered cubic unit cells, how we can calculate based on the formula. In the next slides it will come, no need to worry about that how the 68 percentage will came. Okay, so what is packing in a solids? So first of all, packing efficiency means we have discussed. Packing means what is packing will be in a solid. If you'll see clearly here, the crystalline solids exhibit a regular and a repeating pattern of constituent particles. The diagrammatic representation of three-dimensional arrangements of constituent particles in a crystal, in which each particle is depicted as a point in space, is known as a crystal lattice. Already yesterday we have seen the crystal lattice structure, how the atoms, how the lattice points are being occupied by the atoms or ions or molecules will be. That is what a packing in a solid will be. In a crystal lattice, the atoms are very closely packed, leaving a very little space between them. We have seen yesterday the lattice points are joined uh, joined by a straight line. By those lattice points, if you have considered in the box type of manner structure that we have taken as a unit cell, by the combination of unit cell, we are going to get a crystal lattice that becomes a solid. This is what a packing in a solid will be. Lattice points and lattice, crystal lattices, unit cells. These are all will be present in there. So this is what how the packing is going in a solid will be. Okay, fine. Next. So, and the packing may be available not in a zigzag manner, not in a in their what exactly their well, the packing will be available in a well defined manner. That means what, the packing may be available in three ways, that is in one dimensional, and both two dimensional and three dimensional will be there. So if we will see this, what, once you observe the diagram clearly what he has mentioned, it is in packing in one dimension. We have three dimensions, x and y and as well as z will be. So if we will see, there is only in a one dimension. See, one a straight line represented like this. In that straight line only, in one direction only, these are the atoms or ions or molecules are arranged clearly. Let we will go. So that means what, one atom after another atom after another atom, like that, what, these are packed in a unit cell. Okay, so this type of packing may be available in a unit cell. Okay, fine. Then see this close packing in crystalline solids in one dimension. So this is in one dimension, not only in one direction. This packing is happened in a unit cell. So this type of packing may be available in the unit cell. In one dimension close packing, spheres are arranged in a row. See that in a row, these are the spheres are arranged or not? Yes, arranged in a row such that adjacent atoms are in contact with each other. Once you observe, children, clearly, each atom is in contact with the adjacent atom, and this atom is contact with this atom, this atom is contact with this atom. So every atom is in contact with its adjacent atom or not, in contact with each other. Yes or no? Right. Now the coordination number. So what is the coordination number of each atom? If we will see clearly, you can only say, for example, if you have taken this red color atom you are considering, this is attached with this one, and the same this is attached with this one. So this red color atom is attached with the beside molecule, this beside atom it will be, and this is also again it is attached with this one also. Because of that reason, the coordination number of this middle atom is how much we can say easily? 2 will be. Why? Because the middle atom is attached with this one and as well as this one. So the coordination number of the atom will be what? 2 will be. Similarly, if we have seen, for every atom the coordination number we can say easily it will be 2. Yes or no? Right. In case of one dimensional close packing, the coordination number is equal to 2. Clearly it was mentioned and already we have discussed that. Okay, it is called as one dimensional packing and the coordination number equal to 2 will be here. Okay, fine then. So it is about what? Packing in one dimension. So what is packing efficiency we have discussed, and what is packing in solid we have discussed. After that, what? Packing may happen in three ways: one dimensional, two dimensional, three dimensional. One dimensional is completed. Now we are going to discuss about what? Two dimensional way. How the two dimensional packing is going to be happen? Let us discuss. In a two dimensional close packing, a row of close packed spheres are stacked to obtain a two-dimensional pattern, this stacking is done in two ways that we will see with the diagrammatic representation also. Before going to that, in the two-dimensional packing, we are going to get a square close packing structure. We are going to get how we are get this square close packing. We will see. The second row can be placed exactly below the first row in a close packing. He is saying. Let observe, children, once. A second row is exactly placed. This is the first row. Okay. This is it will be the first row. Okay. And the second row is exactly placed below the first row. You are observing or not? And the third row is exactly placed below the second row. And the fourth row is exactly placed below the third row. In that manner, if you are keeping in a two-dimensional manner, once you take a point here, if we are taking a point here, this is X direction and this is a Y direction. Both directions we are having or not, X direction as well as Y direction. So in a two-dimensional manner, we are going to keeping this. Once again, we'll go with the matter. So the second row can be placed exactly below the first row in a close packing. Thus, if we will call the first row as A type and the second row being arranged exactly the same as the first one, so is also of A type. Similarly, we have seen in the diagram, both rows are A type only. Yes or no? In such an arrangement, each sphere is in contact with the four other spheres. That I'll explain in the diagram. Hence, it has a coordination number is equal to 4. We observe that if the centers of the four immediate neighboring spheres are joined, a square is formed. This type of packing in a crystalline solids are known as square close packing in two dimensions. So if we will see, hence, it has a coordination number is equal to 4. We observe that if the centers of the four immediate neighboring spheres are joined, a square is formed. This type of packing in crystalline solids is known as square close packing. I'll explain the diagram, children. First of all, we have taken a row which is we are calling as A, and in this row we are having the atoms like this, and in the second row the same type of arrangement is there, and one atom is exactly placed at the same below the same atom. This is also below the same atom. This is also below the same atom. If you have taken a atom in the rows, what we have like this, if we have taken an atom, this middle atom is coordinated with how many atoms? Top one atom, down one atom, bottom one atom, and as well as left side one atom, and as well as right side and as well as a left side. So one atom is exactly coordinated with how many atoms are there? 4 atoms are there. But whereas in case of one dimension, we have got that what only with the 2 atoms. If in one dimension the coordination number will be 2 only, but whereas in case of two-dimensional way, the coordination number will be what? 4. Clearly we can see here. Okay, with how many atoms a single atom is going to be coordinated, attached with that, joined with that, that is called as what? Its coordination number. And we will see the structure of that coordination attachment. We are going to get a square or not, it is getting a square close packing. These are all atoms are closely packed, and we are getting a structure. What type of structure we are going to get? Square type of structure we are going to get. Because of that reason, it can be called as what? Square close packing. And this dimension is what? A two-dimensional way. Because of that reason, we can call it as what? Square close packing in a two-dimensional way, we can call it. Okay, so clearly the arrow was mentioned there once you observe. So it is called as what? Square close packing in a two dimensions. Okay, children, right? Then fine, we'll go with the next one. One dimensional is completed. After that, two-dimensional way is also completed. In a two-dimensional way, got square close packing. After that, we are going to discuss about what packing in two-dimensional. We got us what it is what in square two-dimensional way. Two-dimensional way, we got square close packing. So here one more packing is available. That is what? Hexagonal close packing. If we are taking the same type of rows, if you are getting A type of rows, if you are going to get, we are getting a square close packing here. Yes or no? Now we are taking what? The second row can be placed below the first row in a staggered manner. But such that its spheres fit in the depressions of the first row. Thus, if we will call the first row as A type row and the second row being arranged differently can be named as B type. Again, the third row appears as A type. This type of packing is referred to as AB type. And in such an arrangement, each sphere is in contact with the 6 other spheres. Hence, it has the coordination number is equal to 6. I'll explain with the diagram, children. You will be better understanding based on that. That will go with a diagram. Okay, fine. So what he said in a two-dimensional, this is also a two-dimensional way. Initially, what we have seen, this is a type row. In previously square close packing we have seen, and this is also A type in the previous square close packing. But in a hexagonal, once we have observed that it is a B type. All the atoms are arranged in this manner. And in the previously what we have seen, in this ones you observe A below A only there, and below the atom the same atom, below the atom and the same atom will be present, and the arrangement also will be in the similar manner as usual like the upper layer. Yes or no? But if we have seen here, the arrangement of the layer is not in the similar manner. It is a B type, and the next layer will be what? Exactly not below the B. It is started from the, here mentioned as one word is mentioned, depressions of the first row. What is depression? The next layer is exactly placed at the depressions of the first row he is mentioned. What is depression? Depression in the sense what we are getting a cave like structure, the space what we are going to get in between the two atoms, at that place the atom is placed. This is called as the depression area. So at that place the row will be started. So every depression area one atom will be, every depression area one atom will be there. This is the depression area, one atom, and this is the depression area, another atom, this is the depression area, another atom, like this. And the similarly third row if you are going to observe, this is the depression area, this is the depression area, like that what every area will be. So arrangement will be not like the square close packing. So exactly what the arrangement we can say that not exactly like a square close packing. Upon each atom below, no other atom will be there. In a different arrangement is there in a two-dimensional manner. If we have seen here, we observe that the center of the 6 immediate neighboring spheres are joined as hexagon is formed. This type of packing in a solid is known as hexagonal close packing in a 2 dimensions. It has lesser free space and hence higher packing efficiency in comparison to square close packing. Now once we see children, exactly if you have taken an atom clearly, this atom is in contact or coordinated with how many atoms? You only count once. If we have seen here 1, 2 and 3 and 4, after that 5, then 6 will be. So the each atom is coordinated with 6 neighboring atoms or not. Because of that reason, it is called as hexagonal closely packing. Hexagonal closely packing we can call hexagon close packing, 2-dimensional manner. And the coordination number, if we will see, this atom is coordinated with how many atoms? None, 6 atoms. Because of that reason, the coordination number of this atom will be what? 6 will be. Similarly, if you have taken any this atom also you can take. This atom is coordinated with what? 1, 2, 3, 4, 5, 6. Any atom if you can take, definitely we will get the coordination number will be 600. Okay children, we will revise. Initially today we have started with what? Packing efficiency. What is packing efficiency? We have discussed, we got a formula of that, and after that packing how it is going to be happen in the solid. Then after that what? Packing in a 1-dimensional we have discussed. Packing in 2-dimensional in 2 ways. In 1-dimensional the coordination number will be 2, and in the 2-dimensional we are having the coordination number of 4 with square close packing, as well as in the 2-dimensional way another close packing, that is hexagon close packing with the coordination number 6 will be, and it is a type of structure as what? AB type. But whereas square close packing will be what? AA type. AA type we are having the coordination number will be 4. AB type we are having the coordination number will be what? Hexagon close packing, as well as what? Coordination number will be 6 then. Okay, now we will discuss about what 3-dimensional close packing. What is 3-dimensional close packing? We have to get in all the directions, that is XYZ directions. So we will discuss about that. 3-dimensional close packing from 2-dimensional square close packed layers. So this 3-dimensional close packing from the 2-dimensional we are going to get. What is that? Let me see. In this kind of closed solid packing, the second layer is placed over the first layer. So what is saying that the second layer is going to be placed on the first layer in such a way that the spheres of the upper layer are exactly above those of the first layer. So in other words, spheres of both the layers are perfectly aligned horizontally or vertically. We will see that with a diagrammatic representation. Clearly, you can going to observe. Okay, we will see here. Just a minute. Okay, let us name the arrangement of spheres in the first layer as A type. Since all the layers have the same arrangement, now in the previous conditions, what we have seen, one layer below another layer, one layer below another layer, that is in one dimension. Sorry, one dimension only, one layer, every atom is side by side of another atom, like that it will be there. But if we have seen in the two-dimensional, what, one layer below another layer, that is AA type and AB type, both we have seen with hexagon packing and square close packing. But here in a three-dimensional manner, what he is saying that arrangement of one layer upon another layer will be. So what is saying, let us name the arrangement of spheres in the first layer as A type. Since all the layers have same arrangement, the lattice can be observed to follow AA type. So this is the first layer if you are considering A type. Upon this layer, another layer is kept like this, AA. Upon this layer, another layer. Upon this layer, another layer. Like that, if you have observed that in every direction, the middle atom, if you are taking here clearly, here we are keeping upon one layer, another layer we are keeping with the atoms will be. At that time, what? In all the directions, what? X direction as well as Y direction as well as Z direction, in a three-dimensional way, the arrangement of layers, arrangement of atoms will be there. The packing is available in all the directions. Because of that reason, it can be called as 3D. That is what a three-dimensional packing we can call. And the arrangement here we are calling as what? A will be in X direction, Y direction and Z direction. And upon one layer, another layer will be there. In every direction, if we have seen, this is layer, upon this layer will be there. Upon this layer, another layer will be available. Okay, this is called as what? A three-dimensional layers arrangement will be. Okay. After that, in this what? In three-dimensional close packing, if we have seen, upon one layer, here you are going to observe we are having the first layer and as well as the second layer. So three-dimensional close packing from two-dimensional hexagonal close packed layers, we'll observe. Once you observe, children, clearly you are observing here the black color layer, it is observed, it is given black color layer. Whatever the normal lines with a light color lines will be, light color atoms below this thicker lines, light color lines, which is mentioned as layer 1 and down. This is what a first layer will be. Upon this first layer, we are keeping this another layer will be. The thicker lines will be the second layer, that is mentioned as a layer 2 here. That is mentioned as layer 2 here. The thicker layer will be thicker spheres. The thick red color spheres are the second layer, and light red color spheres are the first layer. Just observe the first layer once. We are observing the first layer once. Upon this first layer, the second layer is kept like this. Okay, this is the second layer. The thicker red color spheres are the second layer, and the light color spheres are considered as the first layer. So upon the first layer, we kept the second layer will be. So here it was mentioned O and as well as T. Clearly it was mentioned T, O, T, O, T, O, like that. These are all T's are there. These are all O's are there. Again T will be there. O will be there. What is this O and what are these three? T will be. What we have completed till now. So packing efficiency, packing in solid out will be one-dimensional packing, two-dimensional packing, two types, hexagonal and square closing packing. And after that, three-dimensional way also we have completed. Okay. And in a three-dimensional manner with possible two-dimensional layers, if we have seen, this is a three-dimensional manner only. But packing will be what? Two-dimensional, possible two-dimensional way. So what we are going to get in this from two-dimensional hexagonal closed packing layers, if you are going to observe, I'll explain you. In this kind of close packing, a second layer similar to the below layer is placed in such a way that the spheres of the second layer are placed in the depressions of the first layer. So depressions already I told. wherever the empty space which is available with the first layer, that is called as what a depressions will be. Since the spheres of the two layers are aligned differently, if the first layer is termed as A and the second layer is termed as B, we noticed that a tetrahedral void is formed wherever a sphere of the second layer is above the void of the first layer will be. It will go with the diagram once again. So the normal lines, light red color lines are the first layer we are considering, and the thick red color spheres we are considering as the second layer. When the second layer is going to place on the first layer, at that time, wherever the depressions of the what here we are clearly you can see here the second layer or plane. Since the spheres of the two layers are aligned differently, so here you can observe two layers are aligned in a different manner. It means what? Not exactly that layer, the second layer is not exactly on the first layer. These are aligned in a different manner. This is here started and the second layer is started from here. So these two are arranged in a different manner or not? Yes. Since the spheres of the two layers in and the second layer can be termed as B will be. Okay, fine. We notice that a tetrahedral voids are formed where a sphere of the second layer is above the void of the first layer will be. So here we are going to get as what once you will observe. Here we are going to get a tetrahedral void. Why we are calling a tetrahedral void? What is the reason behind of that? Why we are calling a octahedral void? Once we will see the diagram, what I am keeping here. So here once you see voids representation is here. Here the first layer that will observe where T it is there. The second layer, 3 atoms are here. The second layer, 3 atoms are here. And after that, in between these 3 atoms, a empty space is coming or not? In between these 3 atoms, empty space is there. Here also empty space. Here also empty space is there. Here also empty space is there. Here also empty space is there. Okay. So wherever we are going to get an empty space, that space is in contact with how many atoms will be? With 4 atoms. How it can be called as 4 atoms? Sir, it is only 3 atoms only present now. You get a doubt. Why? Because red color, thick red color spheres only we are having 3 only. This is 1 and this is 1 and this is 1. Total we are having how many atoms with T? 3 only. But backside in the first layer, if you are observing, the first layer, one more sphere is there or not? So total how many spheres are there? Total 4 spheres are there. Once you observe, these are the 3 for the second layer. These are the 3 for the second layer. And this one is from the first layer, which is with a lighter red color lines. At that time, we are going to get empty space or not? So if we will draw the diagram, a tetrahedral structure we are going to get. We will see here like this. So that's why we are calling it as what? A tetrahedral whole. Otherwise, a tetrahedral void also we can. Void is nothing but what? Empty space. Empty space it is which is provided, that can be called as what? Void, which is in the shape of tetrahedral. In a tetrahedral shape, the void we are going to get like this. That's why we can call it as what? A tetrahedral void will be. So in that manner, tetrahedral voids are forming here. In three-dimensional way, tetrahedral void is formed here like this. Okay, so we got tetrahedral void which are represented with a letter of a T will be, which is in coordinated with how many spheres are there? With the 3 spheres of the B layer and 1 sphere of the A layer will be. Okay, children, right. Next, we'll go with the second octahedral void. How we are going to explain that once we'll see. Whereas at other places, we observe that the triangular voids in the second layer are above the triangular voids in the first layer, such that the triangular shapes of these do not overlap. Such voids are known as octahedral voids and are surrounded by 6 spheres. And these octahedral voids are surrounded by how many spheres? 6 spheres. We will see whether 6 spheres are present or not with the octahedral void. We can easily calculate the number of these 2 types of voids. Let the number of closed packed spheres be n. So we can calculate the number of voids in a given crystal lattice also. How it will be if let the number of closed packed spheres. If the number of spheres, if we will know that can be considered as n, then the number of octahedral voids also will be generated n only. That means what? number of closed packed spheres will be 10. At that time, octahedral voids will be generated 10 only. Then tetrahedral voids formula is what generated will be 2n. That means what? The number of closed packed spheres will be 10. At that time, octahedral generated voids n will 10 will be, and the tetrahedral voids generated are 2 into 10. That means 20 will be. So placing the third layer over the second layer. So here once you will see octahedral hole, how we are going to get. Similarly, in this manner only we are going to get octahedral hole. So here 3 spheres are there. Middle of that we are getting the space that is a void. But why we are calling it is an octahedral? It is a tetrahedral. It is octahedral we are calling. It is a tetrahedral we are calling. Why? Because 4 spheres are in coordinated with that void. Because of that reason, it can be called as a tetrahedral. And here if we have seen 3 spheres of the first layer and 3 spheres of the second layer will be. Once you have seen here clearly, 1, 2, and 3. And this is 4, 5, and 6. So 6 we are going to get or not? Let we will see in the diagram. Exactly we are going to get 6 or not. Let we will see here. So let us observe this octahedral void. Okay. So first of all, we are observing with the second layer. Once you observe clearly, this is the first sphere with a thicker line on the second layer. This is the second sphere, and as well as the third sphere we got. So 3 we got. Okay, no problem. And the remaining how many other? Let we'll observe. In the first layer with a light color lines it will be. So with this O, we are having the fourth sphere, and we are having the fifth sphere, and we are having here sixth sphere. Yes or no? So because of that reason, it can be called as what? Octahedral voids will be. In a three-dimensional close packing with a possible two-dimensional close pack layers, we get voids. Those types of voids we have in this lesson are what? Tetrahedral voids and octahedral voids will be. Okay, children. After that, and how can we cover these voids? Very empty spaces we are going to get now. We are getting the empty spaces in the crystal lattice now. Then how can we fill that? How can we close? How can we cover the tetrahedral voids? If we will see here in this kind of close packing in solids, if we will observe that the spheres of the third layer are exactly aligned with those of the first layer. Thus, if we name the first layer as A, if we name the first layer as A and second layer as B will be, and the third layer can be again named as A, he is saying. Okay, so we got as what type of packing efficiency is there? One dimensional coordination how much, two dimensional how much, 4 and 6 will came, three dimensional also there, but in three dimensional we are going to get voids will be, and those are the empty places, empty spaces can be covered or not? Yes, those are the empty spaces. That is nothing but covering of voids. And voids are generally two types. Those are what? Tetrahedral voids are there as well as octahedral voids are there. How can we cover the tetrahedral voids? We will see. So it is first of all we are taking let us consider A layer. After that, what layer will be there? B layer will be there. Then exactly after that, what layer will be there? A layer will be there. So whatever we got a void, that may be covered by the same layer. So how it will be? Let me explain. Solids, the spheres of the third layer are exactly aligned with those of the first layer. Once we will see, if you are considering this is the first layer, the void whatever will be formed here, the void whatever is forming here, that can be exactly filled by the third layer here. If you are considering this is the first layer and this is the third layer will be, exactly it is filled by the this one will be. That means what? Once you see here, if you are considering A is the first layer, the second layer will be what? B will be, and the third layer will be what? A will be. So whatever the void which it is formed here, that is exactly filled by what? The third layer, the same layer which it is formed. Because of that reason, it is going to be filled by the third layer, covered by the third layer will be. Okay. So once again, I'm reading the spheres of the third layer, this one, are exactly aligned with those of the first layer. This is exactly aligned with the first layer will be A, B, A. So this is first and second and third. If we are considered, third is exactly aligned with the first layer. Thus, if we name the first layer as A and second layer as B, and the third layer again changed as what? A will be. So this pattern, like what? If you are observing the pattern, A, B, A, B, like this, what A, B pattern is available. So while covering the tetrahedral voids, what type of pattern we are going to get? A, B pattern we are going to get. This pattern can be written as A, B. This structure is better known as hexagonal closed packed structure. So this type of arrangement we are going to observe in a HCP clearly. Okay, in hexagonal closed packed structure, we are going to observe the covering of tetrahedral voids, and the pattern will be what? AB pattern. That is nothing but those are what are layers of the atoms will be. No need to confuse about it. These are the layers of that which contains the atoms. And the tetrahedral void, whatever it can be used by the third layer. Why? Because the same alignment will be there. Because of that reason, that can be closed. Okay, fine then. So this is about regarding what this is a HCP structure, and AB type of a structure will be there. This is about the covering of tetrahedral voids, how we are going to cover the voids clearly. Now we can discuss about what covering of octahedral voids. So what are octahedral voids? Already we have discussed the void which it is in coordinated with the 6 spheres, that it can be called as what octahedral void will be. Then how the void can be covered. We will see that. See, in this kind of close packing, the spheres of the third layer are not aligned. See, once you see clearly, in this kind of close packing, the spheres of the third layer are not aligned with those of either the first or the second layer. In the previous tetrahedral voids covering area, we have observed that the first layer is covered. The first layer is aligned with the third layer. But in this case, the first layer is the third layer not aligned with those either the first or the second layer clearly. Thus, if we name the first layer as A and the second layer as B, this is the first layer, A is the first layer and B is the second layer, then C is the third layer will be. If we have taken in the octahedral voids, if we have seen A is the first layer, C is what? A, and the pink color layer will be the B, and the green color is what? C will be. Again, what we are going to get? A will be. So A, B, C. After that, A, B, C. Like that we are going to get in octahedral voids will be. So thus, if we name that the first layer as A, this one, and the second layer as B, this pink color one, and then the third layer will be named as what? C will be. This pattern of layers can be written as ABC, ABC, ABC will be, ABC will be. Like that, this crystal structure is called as cubic closed packed. CCP we can call cubic closed packed or face centered cubic, FCC. Cubic closed packed, otherwise we can call it as what? FCC will be. And how the voids are covered, once we will see clearly once again. Here, this kind of close packing, the spheres of the third layer, what is the third layer here? This is the third layer, are not aligned with the, are not completely aligned with those either with the second layer or with the first layer. So third layer, whatever it will be present, C is not aligned with this one, not aligned with this one. Because of that reason, what will happen? See once, here one atom only will be there. And here what? So this is started with 1, and here 2 second row, and third row will be 3. But whereas in case of 3, what first we are having 3, then 2, then 1. It is opposite to this, both will be 3, 2, 1 it is there, but 3, 2, 1 from the back side. Here 3, 2, 1 from the front side. Because of that reason, the voids, whatever it will be present, they can easily cover. The void, whatever it will be here, these are the atoms are going to be inserted clearly into this, and the void is clearly covered. We can able to see here the void, whatever it is going to be formed, that can easily covered by the this layer will be clear. Okay, that we know that. Otherwise, from the downside also, this is going to be covered. This is clearly we can observe that the void is covered from the bottom and as well as from the top onwards also. So in this manner, what the ABC type of a packing will be available in this crystal. That is what FCC and or we can call it as CP. As CP structure in tetrahedral covering, and octahedral voids are covering. We can observe in what especially what is that? CCP and FCC will be. In both of them, the coordination number is 12. as each sphere is in contact with the 12 spheres. If we will see, the coordination number of each sphere will be 12 spheres if we have seen. Okay, then after that, the 74% space in the crystal is filled in this kind of close packing. How this 74% we got? In the first slide also we discussed 68% of FCC I told. And in this what 68% in some and 74% in this. So how these percentages we are going to get, that we will discuss, and how we are getting that percentages, I'll let you know that. So covering of octahedral voids are finished, as well as covering of tetrahedral voids also completed. Then we'll go with the next topic. So let's come on to the new topic, children. Already that what we have discussed earlierly, packing efficiency calculation, I told how we are getting the percentages will be. Already this was discussed yesterday, but once again I'm saying that packing efficiency, how we are going to calculate. So the packing efficiency of different lattices, centered lattices, simple cubic lattice, body centered lattice, and as well as a face centered cubic lattice, how we are going to discuss. After that we'll see once. So packing efficiency formula is what? Volume of one atom into 100% by volume of cubic unit cell. So if we have taken a simple cubic unit cell, we are having volume of one atom will be, that is, it is a sphere. Because of that reason, what is the volume of a sphere will be, that we are taking as what? 4/3 pi r cube. Volume of one atom is in a sphere manner, that's why 4/3 pi r cube if we had taken, that is, instead of volume of one atom we are considering as 4/3 pi r cube into 100, as usual we have written. And volume of a cubic unit cell, in the sense what? The volume of a cube, if we have considered a into a, because of that reason a cube will be. So total what? A cube in the sense 2r we are considering. Why we are taking 2r? So especially 8r cube we are got here. Volume of the cubic unit cell we got 8r cube. Why we got 8r cube? Volume of the cubic unit cell formula is a cube. That is, a means what? Here simple cubic lattice, the edge length a is equal to 2r will be. That already in the IIT class I told, a is equal to 2r. That already yesterday class I have discussed. So instead of a we are taking 2r will be 2r whole cube we get. 2r in the sense what? 2 cube means 8, r cube we are going to get into 100. By the simplification we are going to get as what? 52.4% packing efficiency is available in simple cubic lattice. The remaining percentage is what then? The voids, whatever we are going to get in that, and that is the vacant or the loss we can call clearly. Okay, this is about simple cubic lattice packing efficiency. And in the second case, if we have taken here volume occupied by 2 spheres in the unit cell, 2 into 4/3 pi r cube here considering. Why he has taken 2? Already we know that BCC, in BCC lattice, how many atoms may exist? At the body centered, one atom will be there. At the corners, 1/8 part of each atom is contributing by the unit cell. Because of that reason, we are going to get 1. So total atoms present in the BCC, already we have discussed. Because of that reason, total atoms present in the BCC, what? 2 will be. Number of atoms, already in the first slide we have seen the formula. Number of atoms into volume occupied by the spheres in the unit cell. So 2 into volume what? 4/3 pi r cube. 2 atoms into its volume. So 2 into 4/3 pi r cube. And the total volume of the unit cell in the BCC will be 4/√3 r. Already we have seen that. So 4/√3 r into whole cube, the volume of the cube, that's a cube we have taken. A is equal to 4/√3 r. Because of that reason, 4/√3 r whole cube into 100 will be. Then we will do the simplification. Packing efficiency, what we are going to get? 68%. Okay, children, now we got the 68%. First slide, what we have discussed is 68%. Now that 68% we got in this manner. Okay, this is the 68% will be. Then afterwards, the next one will be what exactly? Packing efficiency in the CCP and HCP lattice. So this is what a volume occupied by one unit cell, 4 into 4/3 pi r cube. Why? In CCP, HCP, already we know that how many number of atoms are present. Face centered, it will be what we are having CCP and HCP. All the 6 faces are contributing half of the atom. Because of that reason, what? 6 faces into half of the atom. 6 into 1 by 2. You are going to get as what? 3. And corners are contributing 1 atom. Because of that reason, 3 plus 1, 4 atoms will be. So that because of that reason, we are taking 4 into 4 by 3 pi r cube. And edge will be is equals to 2 root 2 r. Because of that reason, we have taken 2 root 2 r. Edge relation in between edge and the radius, if we have considered 2 root 2 r, already we have seen yesterday. That is 2 root 2 r whole cube we got. So because of that reason, 16 by 3 pi r cube. 4 4s are 16 by 3 pi r cube. And it will be what? 2 2s are 4. 4 2s are 8 we are going to get. Then what? The simplification, if you are going to get as what? 74% of packing efficiency in CCP and HCP lattice we are going to get. This is about the packing efficiency of BCC, HCP and CCP will be. Okay. So in this manner, what we are going to get the packing efficiency, already what we have discussed in the first slides, initial slides will be, once you observe clearly. This is the packing efficiency, what we have said. Body centered cubic unit cell 68%. I told now how we got this 68% I told, and what formula we have used till now, 4 by 3 pi r cube by 4 into that number of atoms into volume of the occupied. This formula we have used. Number of atoms, that 1, 2, 4 in the particular unit cell into volume occupied by one share into 100 by total volume of the unit cell, that we have used that. Okay, so this is the case. And after that, the next topic. So solids we have completed, matter, types of solids, crystalline solids, amorphous solids, metallic, ionic, molecular. These are the crystals we have completed. And after the Bragg's equation we have discussed based on the problems we completed. After the Bragg's equation, based on the diffraction phenomenon, the crystal properties, how we can calculate the distance, glazing angle, as well as the wavelength of the X-ray radiation, that we have completed. After that Bragg's equation, we have discussed what type of solids packing is their coordination number, density of the crystals. Density of the crystals we have discussed, all as well as what how the packing efficiency will be calculated, packing fraction how we have calculated, and contributing of atoms with different lattices. What is lattice? Crystal lattice, lattice point, how many types of primitive unit cells, body centered unit cells, along with that packing, what unidimensional packing and up to 3-dimensional packing, and what are the voids and how the voids can be covered, that also will discussed. And packing efficiency formulas also we have completed. Now we have entered into the topic of what defects in the solids. What is meant by defects exactly? So defects in the solids can be, this is the important topic regarding IP. Children, in this lesson, majorly we should focus regarding IP. If we have seen Bragg's equation as well as defects in the solids, majorly we are going to get the questions from this lesson, these topics only. Okay, so we have to focus in this. So we'll see the definition of the defects in solids. What is meant by defect in the solids? Solids are formed from many small crystals, that we know that. However, during the process of crystallization, the defects in the solids occurs due to the fast or moderate rate of formation of the crystals. Might be what some of the crystals may form very eagerly, very early. Some they are going to form very slowly will be. It depends upon the nature and depends upon the arrangement, bonding nature it will be. So defects in general is meaning of that are defined as those in which there will be irregularities in the arrangements of constituent particles. On the basis of irregular arrangement, the defect may be a point defect or a line defect. So defects nothing but you don't think as what something is happening there like that. Defect is nothing but what the arrangement might be not in a proper manner. Might be some of the atom is missing at one place. Instead of one atom, another atom is coming there. This type of things normal ga undalsindi normal ga undakunda in very different manner lo untundi. That means nothing but what exactly the atom, it should be there in one position. Might be that atom should not be there. An ion should be there, that ion should not be there. Maybe a vacancy, might be a vacancy should be present. Might be another ion should be present. So that type of things generally called as what defect will be. So in an ideal crystal, when there are any irregularities, so we are observing irregularities in the arrangement. Actual arrangement kakanda irregular arrangement will be there. So that type of irregular arrangement can be called as a defect in the crystal. So irregularities of arrangements around any point or any atom in the crystal, then it is said to be deviation point defect. Likewise, when there are any deviation arrangement in the entire row of lattice points of crystals, then such type of defect will be line defect. So what is, we are having two types of defects will be line defects and point defects. So what are line defects and what are point defects? Let me see. Here in an ideal crystal, when there are any irregularities of arrangement around any point or any atom in the crystal, when that is said to be a deviation point defect. If the irregularity, if you are going to observe at any point and any atom in the crystal, that is a point defect. When there is any deviation of arrangement in the entire row, the complete row is defected, that complete row is deviated from the structure lattice points of the crystal, then such type of defects can be called as what line defects. If we have observed any atom, a single ion, a single molecule is deviated from the regular arrangement, that type of defect can be called as what point defect. If the total layer, that is unidimensional layer, like that three-dimensional layer, the total line, the total row, entire row when we having a deviation, that type of defect can be called as what it will be a line defect. Okay, so we are having crystal defects. If you observe clearly, defects in solids, how many types of defects are there? Line defects and point defects already we have defined it. And if we have seen clearly, in line defects and point defect, crystal defects are line defects classified into point defects, and line defects are edge dislocation, screw dislocation defects classified, and point defects are furtherly classified into stoichiometric defects, impurities defects, non-stoichiometric defects, and again stoichiometric defects are Schottky defects, Frenkel defects, interstitial defects, vacancy defects. And these non-stoichiometric defects are metal excess defects, metal deficiency defects. And these metal excess defects furtherly what? Presence of anionic vacancies, presence of a cationic interstitials will be. And these are the defects along with electrical and magnetic properties of the solids. 2-3 topics are left over. These are the 3 topics. Tomorrow we are going to discuss about the topics. Okay, children? So definitely everybody try to listen the classes from the starting onwards. Don't miss the class and don't skip the class. Whatever the class it will be. On the sequence manner, you try to listen, then you will better understand. Okay. So thank you, children. Today we're going to stop the topic up to here, and the remaining class to be continued by tomorrow itself. Okay.